36.4. This video we're going to use our calorimetric method to determine the enthalpy change of neutralization. Before that, we'd like to show you a QR code, to show you a calorimeter, how a calorimetric method can be used to determine the standard enthalpy change of combustion, To determine the enthalpy change of neutralization, we'll use the method called direct measuring the temperature change of reaction mixture. For example, in these situations, we have used HCl and NaOH, So we just add this acid and alkali into an expanded polystyrene cup, and then we're going to measure the temperature change in the process. As we know that this one is exothermic reaction as well, so we'll anticipate the temperature of the thermometer will just keep on going up. So in this case, we have used a few apparatus. The first one is expanded polystyrene cup. So this one is a good heat insulator, so therefore it just help to reduce heat loss to surroundings. You should have the word surroundings behind. While the other ones, you can see that other than the expanded polystyrene cup, we also have some we have a beaker right there to hold the expanded polystyrene cup, and we also got some cotton wool right there. So actually the cotton wool and also the air trap in between, it is also used to reduce heat loss by conduction this time. So we have a stirrer as well. The stirrer is just to ensure the heat is evenly distributed in the water. So this time we because we are also talking about standard enthalpy change of neutralization, so the unit still to be kilojoule per mole. So what we are doing, we just have the energy release, using the same equation, E equals to mc delta T. E equals to mc delta T, and also we have to find out the number of mole. But if you remember the definition for neutralization, the number of mole that we are talking about is the number of mole of water. So therefore we have to find out the number of mole of water formed in the process. And the one above, our E equals to mc delta T, the C and also the M, we should be talking about the mass of the solution and also the specific heat capacity of the solution. So the solution, normally we'll consider as a reaction mixture. But if you know that, the reaction mixture, actually it is not pure water. But most of the time, we do have assumption. We assume the reaction mixture having the same specific capacity and also density as that of water. So that will be the assumption that we have, same as that of water. So we assume the specific capacity, the density of the reaction mixture same as that of water. So this is our assumption. So it will be like that. Using the mc delta T, over the number of mole of water formed. And remember, this is neutralization, so it have to be negative all the time. So because we know that enthalpy change of neutralization is roughly around negative 57.3. So when we do the calculation, you will find that, if your answer is more negative than this value, normally you have a wrong calculation. If it is far or less exothermic than this one, maybe like negative 10 kilojoule per mole, then you have to check whether you're dealing with a strong acid, strong alkaline, or you have dealing with a weak acid and weak alkaline. So extra things that you have to think of, would be a limited reagent problem. So I'll have a look at first example. So right now, experiments carried out to determine enthalpy change of neutralization. So we got several data right here. So first of all, we will have a volume of 1 m HCl, volume of 1 m NaOH. So we are having HCl plus NaOH right there. And then both of them, they will have 1 m, 50 cm cube. So I convert it to dm cube right away. And then they will just give out NaCl and also H2O. So it should be a 1-to-1 ratio manner. Okay, so the energy, okay, E equals to mc delta T part. Okay, so the initial temperature will be 20 cm cube, okay, and then initial temperature of NaOH, okay, will be 20 cm cube. That means both of them, they are same temperature. Normally it have to be both of them in same temperature, because if they have different temperature, there will be energy transfer. But I don't think this is not a physics question, so therefore we won't have that happen, okay, in chemistry questions. So most of the time the initial temperature will be the same. So the final reaction mixture will be increases, okay, to 26 degrees Celsius. Okay, so the specific capacity, okay, you can see that we have an assumption here, okay, we'll assume, okay, the reaction mixture is the same as water. So you see that, okay, they're using the unit of K, okay, but right here is degrees Celsius. So to remember, convert it into K. And then this one, the mass is gram, but we are not having mass, we are having cm cube. So therefore we have to use density to help ourselves as well, okay. And then the energy will be in joule. Okay, so we'll do the calculation. First of all, okay, we are going to use E equals to mc delta T first, okay, but we have to find out the mass of the water. So the first one, okay, we need an assumption, okay, we assume the density and the specific heat capacity of reaction mixture is the same as that of water. So by using this statement, okay, then we can continue doing the calculation. So we have mass of water equals to density. Density of water is 1 times the volume. Remember, we have add two things together. So this one is very important. Okay, we have add acid and alkaline together. So total will be 50. So make up, okay, this one will be 100 gram. 100 gram. Okay, and then for the E equals to mc delta T, the energy released. So this one is step 0, this one is step 1. Energy released equals to mc delta T. So it will be 100, that will be in gram, 4.2, that is joule per gram per K, and then temperature, that should be 273 plus 26 minus 273 plus 20. Okay, so by doing this, okay, you can find the energy release should be 2,520 joule. Okay, so after that, okay, we will go to find out the number of mole of water. But the number of mole of water, okay, is based on, we have two data, two set of data here. So therefore we have to find out which one is in excess and in limited. But you can see that right here, okay, both of them, they have the same molarity and same volume, and then they are 1-to-1 manner. Okay, so basically, okay, you will find that, okay, both of them, okay, they should not be in excess or limited, they just react just made. Okay, but still we have to find out, we have to calculate to show the others, okay, how we found the number of mole of water. So number of mole of HCl will be equals to mv, that will be 0.05 mole, while the number of mole of NaOH will also equals to mv. Okay, so you can simply say, okay, because 1 mole HCl reacts with 1 mole NaOH, so therefore, okay, number of mole of water will equals to 0.05 mole times 1/1. That means 0.05 mole. So what is this? Okay, this one should be the coefficient, okay, the mole ratio, 1-to-1. Okay, this is 1, this is 1, 1-to-1. Okay, so after we get the number of mole of water, so what we need to do next, okay, will be the energy release, okay, over the number of mole. Okay, so energy release over number of mole. I just continue getting smaller and smaller. So enthalpy change of neutralization will then equals to negative 2520 over 0.05. Okay, so this one, okay, will get up to around negative 50,400 joule per mole. If I convert to kilojoule, that will be negative 50.4 kilojoule per mole. So we just check this one. Is it more negative than 57.3? The answer is no. Okay, so this one is less negative. Okay, so normally less negative we involve a weak acid and weak alkaline, but we can see that okay we are not using weak acid and weak alkaline. Okay, why there is less energy release in the process? Okay, of course there is some of the error. Okay, basically it will be due to the heat loss to surrounding. Okay, so for this one, okay, we'll see that the answer, okay, should be in a sensible range. Okay, so at the end, okay, you just answer, say that okay, therefore the enthalpy change, remember this is not standard. Okay, don't add this symbol. Enthalpy change of neutralization is negative 50.4 kilojoule per mole. Do pay attention, okay? You need to have the sign, okay, at the end. Okay, so that's all how you calculate the standard enthalpy change of neutralization. So basically, okay, you got two exercises you can practice on. Okay, one is self-test 34.2. The other one, okay, that will be class practice 34.5. So pay attention to class practice 34.5. So you can see that actually the data, okay, nitric acid is a monobasic acid where they have 0.5 m and 75 cm cube. Okay, and then you're mixing with 50 cm cube of 0.5 m NaOH. Still, okay, their ratio should be 1:1, but you can see that there is a limited and excess concept in it. Okay, so when you deal with it, okay, you need to tell me which one is in excess. Okay, so you can see that actually in this case, okay, 1 mole and HNO3 we have 1 mole NaOH. So nitric acid is in excess. So you may ask, okay, should we write what we have learned in limited reagent, what we have learned, say 1 mole of HNO3 need to react with how many mole of NaOH, but now we only have, if you can write that, that would be perfect. Okay, but this part, okay, the calculation normally in public exam will be like only 3 to 4 marks. Okay, normally 3 marks only, so they are not expect you to write that much. Okay, you just have to tell them the ratios between the reactants. Okay, like 1 mole react with 1 mole, okay, which one will be in excess. Okay, that will be good enough already, but it is a must to tell the others, okay, what which chemical will be in excess. Okay, so this one, okay, please do this on your. And again, okay, you can just now see that the experimental result is less negative than the theoretical results. Okay, it won't be heating like negative 57.3 kilojoule per mole all the time. You may have like just now like negative 50.2. Okay, so the reasons, okay, sources of error mainly, okay, that would be the first one, heat loss to the surroundings. Okay, not all the energy will be given to the thermometer, so the expansion of the liquid inside thermometer is not really exactly the energy absorbed released, okay, by the reaction mixture. Second one, okay, again we haven't measured heat capacity of expanded polystyrene cup and also the thermometer. Okay, we didn't take that into consideration, and we also assume, okay, the specific capacity and density of reaction mixture. We assume it as the same as that of water, but actually they are not the same. Okay, they are not the same. So to be more precise, okay, we should consider specific capacity and also the density of the reaction mixture correspondingly. And also, okay, it is not carried under standard condition, so if you compare this one, okay, may not be that accurate. So improvement, okay, we can use vacuum flask. Okay, so you can see this one. So vacuum flask, okay, can help us to reduce heat loss to the surroundings. And we can also consider the specific capacity and density of the reaction mixture. Okay, and also we have to take into account, okay, the expanded polystyrene and also thermometer. Okay, so that's what we can do to increase the accuracy of the calculation. So to summarize, okay, remember calculation of standard enthalpy change of neutralization, just like before, you use E equals to mc delta T. Okay, that will be negative, and then over number of mole of water. But you have to pay attention, okay, that may have a limited reagent problems. Okay, so you may have to tell which one is limited, which one is in excess, and the value have to be negative and shouldn't be more negative than negative 57.3. Okay, if you calculate negative 58, I think it will be still all right. Okay, but if you say negative 60 something, that would be too much. Okay, so we have assumption for that. Okay, we assume the density and specific capacity of mixture is the same as that of water. Remember, you also have to sketch this diagram. Okay, sketching is very important. Okay, and sources of error, just as we have mentioned, and also improvement. Okay, so remember, heat loss to surrounding always, okay, it would be the best. Okay, and also you may also consider expanded polystyrene cup and thermometer and so forth and so forth. And the improvement, you may say like use vacuum floss to reduce heat loss to surroundings. Okay, so that's all for this video. We have some more exercise. Okay, we have also a special ways to find out the heat, the temperature rise, okay, in these experiments. Okay, so we'll have a further videos, okay, to explain that situations. Okay, so that's all for this video. Bye bye.